Welcome, this is lecture number 41. In this lecture, we are going to talk about dynamics of switch mode power converter and overview of model based nonlinear control. So, first we will talk about state space modeling of switch mode power converter and different types of model. Under state space modeling also we will get different types of model. Then we will talk about dynamics under switching, large signal as well as small signal model. So, switching model, large signal model and small signal model. Then we will I will talk about the overview of nonlinear control, which can be relate, we can relate the different type of nonlinear control based on what type of model we use, okay. And then choice of model and control method with some discussion. So, first let us consider a boost converter, although we are talking about a practical boost converter first. So, we know that the state vector we consider generally, the current through the inductor we generally consider, and the voltage across capacitor. This we are taking as the state vector. Is a 2 cross 1, right? It is a 2 cross 1 matrix. And we want to obtain x dot equal to AQ x BQ V in. What is AQ and BQ? Because we have a Q variable here, right? And Q can take, it can be either 1 if S is on, the switch is on, right. So, that means if we take F is on, it is equal to 0 if S is off, right. So, depending upon the switch state, we will get Q0 or Q1, and based on Q0 and Q1, you will get A0, A1 matrix based on Q0, Q1 value, right. So, that means we are talking about A1 when Q equal to 1 and A0 when Q equal to 0, right. So, sub interval 1 when Q equal to 1, like in a boost converter when this switch is on and this switch is off, right. So, this path does not carry any current. So, you will have a separate circuit RC branch and we have a separate RL circuit, right. So, you can write down the state equation, the dynamics of the inductor current and the dynamics of the capacitor voltage can be derived, and that we have discussed in sufficient detail. So, I am not going to repeat because under state space modeling we have discussed this. Then we can write the output voltage equation, right, and this can be, in this case the output voltage is simply a function of the capacitor voltage. If we go to sub interval 2 when the switch is off, we will get the circuit. So, this path is off, but this is now on, right. Again we can write the state equation, inductor current dynamics, capacitor voltage dynamics, and we can also write the output equation, which is a function of inductor current and the capacitor voltage. So, overall state space model, we already know A1 when the switch Q equal to 1, which is a sub interval 1, and the sub interval 2 when the switch is 0. So, two matrices we found. Similarly, but interestingly B matrix are common, whether switch on and off, the B matrix is always, that means input is always connected, except for the discontinuous conduction mode where the inductor is turned off because it is not carrying any current, then only B matrix will change. But we are talking about continuous conduction mode. But C1 matrix are different, both A1, A2, A1, A0 are different. C1, in this case the output is direct function of the capacitor voltage, but in this case the output voltage is a direct function of output voltage as well as a part of the inductor current. So, now if we take an ideal buck boost converter, so A1 matrix, that means when the Q is 1 we can get, A0 matrix when Q equal to 0 we can get, okay. So, B1, B2 matrix also you can get, C1, C2, C0 matrix. So, now we can combine this into vector form, that means what is that vector form that we are going to discuss. That means, if we try to write AQ, what is AQ? So, AQ in this case is nothing but, if you see these two matrix, first term is 0, second term is 1 minus Q by L 1 minus q by c minus 1 by rc. Okay, and BQ is simply your B matrix. This is your B matrix. So that means AQ, if we write once again, AQ if we write neatly, 0 minus 1 by Q by L, 1 by Q by C minus 1 by RC. That means when the Q is 1, this is 0, this is 0, so we are getting A1. When Q is 0, then we are getting this. So we can get the overall matrix X dot equal to AQX plus BQ V in, and which we will call as FQ function of X V in, and this is exactly we are writing. It is a function of, okay, it is also function of Q, sorry, it is also function of Q because Q is a switching gate signal which can take either 1 or 0. So this is a function of this. Okay, that means again we write X dot equal to AQX plus BQV in. Since this matrix we have a Q function, so we can get X Q V. But this is a discontinuous vector field because AQ matrix is discontinuous. They are totally different structurally. When Q equal to 1 and Q equal to 0, if you go back, you see this matrix and this matrix are fundamentally different. I mean, if you take the rank of the matrix, the position of this element, you cannot relate them, right? So they are structurally different. Similar, as a result, this vector field, that means if you take F1 and F0, they are fundamentally different. So that is why this is a discontinuous vector field at the point of discontinuity when your Q changes from 1 to 0 or 0 to 1. Similarly, the output voltage will have a discontinuity because in the output voltage, what is the output voltage expression? We wrote that CQ into X plus DQ into D, or you can say V in whatever. So CQ is a discontinuous matrix, and that also C1 and C0 are different. So for ideal converter they are fine. For ideal converter the output voltage is not discontinuous, it is not discontinuous. But if you go to the practical boost converter, we talked about the practical boost converter, that C1 and C0 are different because this term is causing discontinuity. Okay. So in general we can think of the vector field where this is a discontinuous one, the output can be also discontinuous in general. So where Q equal to 1 is the on state and Q equal to 0 the off state, and their duration of on and off is nothing but T on and T off. Now T on and T off are flexible because under steady state we need to achieve a set of T on T off. That means T on and T off, I can think of it is a set, right. So for SW is nothing but sum of T on plus T off, right. So suppose if we choose, and if duty ratio is the duty ratio, if we take T on by TSW, if we want to maintain the same duty ratio, we can choose a different T on and different T off, so that the ratio of this will be, that means what is my D? It is nothing but T on by T on plus T off. So if you want to maintain the T on plus T off ratio to be same, we still can vary T on and T off to achieve in such a way the ratio will be same. So that means in principle we can get infinitely large set of T on T off which will satisfy my steady state requirement. During transient, the choice of T on T off play a significant role in the control because what is my desired transient response? We want to make it fast, we want to avoid overshoot undershoot, how fast we can achieve. So that T on T off will come either from closed loop, in some cases the designer also use a time based control. But whatever it is, there is a flexible, I mean you can flexibly choose T on T off, but there are some practical constraints. T on T off cannot be too small, it cannot be too small even though you keep the ratio same, because if you decrease T on T off, then time period will decrease and your switching frequency, which is 1 by T on plus T off, right. So, if you decrease their value, the sum, then the switching frequency is very high. So, there is a limit on the switching frequency, otherwise losses will be there, there are many other practical aspects. They cannot be too large because switching frequency will be too low and the ripple will be too large. The ratio cannot abruptly change because the duty ratio has a limit. So, upper limit and lower limit, and we have discussed in the steady state loss analysis, even if a boost converter, we cannot achieve in a practical boost converter voltage gain more than 3, it is very difficult, because again the gain will fall. So, there is similarly for a buck converter step down, if we want to achieve a very high step down using a single buck converter with a low duty ratio, there are practical constraints and the losses can be very high, and that is why people try with different architecture to extend the duty ratio either at low or high, whether it is a buck or boost, and there are different topologies. So, there is a practical limit on the ratio of the converter as far as the simple buck and boost converters are concerned, and time period cannot change abruptly. That means, in under one steady state you have one time period, you choose one set of time, suddenly for another steady state you choose another set of time period. So, we cannot change abruptly because we have to design input filter. So, we need to achieve certain desired time period. So, these are the constraints that are imposed by the practical converter, which will limit the choice of T on T off. During transient, we cannot have even very large T on T off, that can result in very high current overshoot and so on. So, it can damage the devices. So, now before we go for the average nonlinear model, that means whatever we discuss is that T on T off, they are basically if we take a standard pulse width modulation, that means okay. So, if we consider this one is a discontinuous vector field which includes switching dynamics. Now, we are talking about the average dynamics, and we have discussed a lot of average model, state space averaging, circuit averaging, where we have considered the average quantity of anything over a time period, right, and we denoted this as a x bar. It can be inductor current, it can be output voltage, state variable, right. So, we can write the dynamics of the any DC-DC converter average dynamics in terms of this. This is a standard for PWM. Then we can separate out A1, A0, and then from here itself we can separate out, you take D part here, D part here. So, A1 minus A0 into dx, then you can separate out, and this whole thing we can write, as a vector. Now, this is average dynamics. Now, interestingly, if we consider FQ, which was, what was that? FQ was a discontinuous vector. That means, we have considered Q into A1 plus, if we go back, if we recall our A matrix, if we consider our A matrix, it was nothing but AQ into X plus BQ into Vin. And what was AQ for an ideal boost converter? 0 minus 1 by Q by L, 1 minus Q by C minus 1 by RC. And what was BQ? It was nothing but 1 by L 0. So, there is no dependency of Q. So, this FQ is a function of Q and it is a discontinuous function. So, this is also vector, but it is a discontinuous vector. But after you apply averaging, that means you are averaging over a cycle, then this discontinuous Q is replaced by duty ratio D. That means, I can say the A average is nothing but 0, 1 minus D L, 1 minus D C, 1 by R C, right. So, this is our vector field where q is replaced by d, where d basically a continuous variable which can take the value typically in the open interval between 0 to 1, because if you set it is 0 or 1, then again we are talking about saturation, deuterium saturation. So, in general if you do not consider deuterium saturation, it is the open interval between 0 to 1. So, this is a vector. Similarly, you can write the expression of output voltage, and this is a scalar, this is a vector, but this is a smooth vector. So, this is a smooth vector, and where it satisfies what is called Lipschitz continuity. So, that we can apply Taylor series linearization. We cannot apply Taylor series here because it is a non-smooth vector field and discontinuous vector field due to the discontinuous control input, but when you apply averaging technique, now it becomes a continuously differentiable function, and then it satisfies the Lipschitz continuity where we can apply our traditional way of Taylor series or other control technique where the continuous vector field or the smooth vector fields are used. Now, we want to do Taylor series. So, any differential equation in general, if it is nonlinear and if it is continuously differentiable, continuously, or at least the first derivative must exist and it will be finite, and the output voltage also can be written, then we can approximate. If it is continuously differentiable, then you can approximate using Taylor series. So, this function can be approximated and at some steady state condition, then it is the partial derivative, this and higher order term, right. And what are the higher order term? If we take the next higher order term here, it will be dou to f average dou x to steady state x tilde square by factorial 2 and so on, right. So, n factorial. So, you can take this to be in general n, this is n, this is n, this is n. So, you can think of nth term. Similarly, for this term. Now, we generally replace that x average can be replaced by the steady state quantity plus a perturbed quantity, right. Now, what is the derivative? We can take differentiate and the steady state derivative is 0. So, this is 0 and steady state quantity again this term will be 0. That means, we started with x dot equal to f average x dv, right. So, under steady state, if we replace all steady state, this will also be at steady state, right. So, this should also be 0, whole thing 0. So, this will be 0, this will be 0. So, you will left with this term, this term, this term and higher order, and if we ignore the effect of higher order term, then this can be approximated and this will look like a linear system model, x dot equal to x plus bu, where u is nothing but the duty ratio here is the control variable. Okay. And this is the perturbed model. Remember, perturbed called small signal model. Why? Because we are ignoring the effect due to the higher order term, and if you take large signal model, large variation, this term will come into picture, your model will drastically deviate, and that we have discussed. So, we can take the vector, these are 2 into, how can we find this Jacobian? How can we find this quantity dou fb? That means, if fab has 2 components, it is a vector, it is 2 cross 1, right. So, if you take, it is 2 cross 1, so it has 2 components f1, f2, those are scalar. And similarly, we have x which will also have 2 components x1 bar, x2 bar, right. Now, how can we obtain x2 bar, second order system, these are scalar. So, how to get this one? This is called Jacobian, where dou f1, dou x1, dou f2, that means if I take a function fav which is let us say f1, f2, initially you consider, and I take another vector which is consists of x1 x2, for example, this is a vector also. I want to get this vector partial derivative with this vector, and this can be written as the first term dou f1 dou x1 dou f1 dou x2. That means in this line f1 should be there in the numerator, dou f2 dou x1 dou f2 dou x2. So, this is exactly what we got, and this is called Jacobian matrix. Okay, so you can find out this Jacobian matrix at some steady state point. If you want to find, you have to find this value. Now, if it is a scalar, if you differentiate, then it is very simple, just dou f1 dou d dou f2 dou d. So, using that we can obtain the Taylor series. Next, output voltage, which also we saw in boost converter, the C equivalent matrix CQ. So, that means we got V0 was CQ x plus something into, in this case there was no other term, so it was fine. So, this C equivalent, what was CQ? We got that it was 1 minus Q into alpha RC into alpha. That means when Q equal to 1, it has a different value. Is for a practical converter, Q equal to 0, it is different. So, this function can also be different, and that's why in a boost converter, when you consider ESR, this is due to the ESR, there will be discrete jump in the output voltage at every switching instant, and this discontinuity is coming due to the switching event. So, then we can again write the Taylor series, but here we are talking about the average quantity. This is average. That means this we write like HQ, but when you take average, when we write this quantity is replaced by 1 minus D alpha RC alpha into X average. So, now there is no discontinuity because this is a continuous variable. Again we can write Taylor series, and again output voltage can be replaced by steady state quantity and the part of quantity. Again you can expand in terms of Taylor series, and now this steady state quantity is equal to this steady state quantity. So, you can cancel these two terms from both sides. Then what is left? And if we ignore the higher order term, then you will get that output perturbation, the AC excitation is nothing but this term into x sum, and this is exactly what C0 and D0. That means the output voltage perturbation is a function of perturbation of the state, and can also be a function of perturbation of the duty issue. Okay. So, now we have considered the perturbation. In fact, we can also consider input voltage perturbation, which you have not considered, but you can follow the same process, right. That means we can follow that, we can obtain that X average dot in terms of F average dot. We have considered only duty ratio, but you can also write V in, and again what you will write, you have to consider another term dou Vf by dou V in into V in tilde, that term you have to consider. And this particular term, if you compute at steady state, this will give you the equivalent matrix, E matrix, supply disturbance. So, now average quantity if you set 0, so this could be at steady state, it is 0. So, you can get this Parter model, and we can take an ideal boost converter. So, now we want to consider linearization, that means you take X perturbation average dynamics, which we call this whole right hand side we call as a F average, which is a function of X average, and average we also replace with this quantity, right. Here also you can write X average. So, this is a function of average quantity D and V in. We can now consider the perturbation, and we can separate out the steady state quantity, and we can get the lineage. So, find the model. Now, we consider a boost converter. So, in ideal boost converter, what is our A1 that we consider? It is like a 0, 0, 0 minus 1 by RC. What is our A2? Our A2 was 0 minus 1 by L, 1 by C minus 1 by RC. Then what is our A average? A average is nothing but D into A1 plus 1 minus D into A2, and which we can write 0 minus 1 by D L, okay, 1 minus D C minus 1 by RC, correct? Then what is my B average? Again D into B1 plus 1 minus D into B0. Since these two matrices are same, so it is simply B, which is either B1 or B0, whatever, they are all equal. So, F average in a boost converter is nothing but, A average into X plus B average into V. What is that? This is nothing but, so if we consider this 0, 1 minus D by L, 1 minus D by C, 1 by RC into X1, X2 plus V in average by L 0. So, which can be written as, if you write it down, so you will get V in average minus 1 minus D into X2 average by L, and this side what you can write, 1 minus D X1 by C minus X2 by RC. So, that means if I write in terms of F1, F2, then what is my F1? It is V in average minus 1 minus D into X2 average by L, and F2 is 1 minus D X1 average by C minus X2 average by RC. Okay? Now, we want to get the Jacobian matrix. That means, what we want to get, obtain? Okay, so we obtain this. And what is the output voltage expression? So, if you take a space here, in output voltage, since we are taking ideal boost converter, it is simply nothing but your X2 average. So, there is no discontinuity, there is no problem. Now, we are, so what I am trying to get? I want to get X tilde of a boost converter is A into X tilde plus B into D tilde, and if you want to also achieve the input voltage perturbation, D tilde, okay, and then V0 tilde is simply your X2 tilde. So, that means your C matrix is, it is already there. So, what is your C matrix? That means we can get C into C0 into X tilde. Now, we want to find out what is my A? It is the Jacobian dou F1, dou X1, dou F1, dou X2, dou F2, dou X1, dou F2, dou X2 computed at steady state. Now, we want to find out what are these. Let us find out what is this quantity. If you go back, Okay. So, what is my F1? So, you can say this is my F1. That means, if I differentiate with respect to x1, it will be 0, right. So, you will get 0. That means, my dou F1 dou x1 is simply 0. What is my dou F1 dou x2? Dou F1 dou x2 is simply minus 1 by d, correct. What is my dou F1, sorry, dou F2 dou x1? So, it will be 1 minus d by c, this is coming from here. And what is my dou F2 dou x2? It is simply minus 1 by RC, correct. So, what we are going to do get, so the first term will be 0, second term will be minus 1 by d into L, third term will be 1 minus d by c minus 1 by RC. This is my A matrix. B matrix, since it is common, so it will be simply 1 by L, because B matrix is common, right. What is B matrix? Okay, no, here it is not that B matrix, it is the B matrix, sorry. So, here what is A matrix? Here A matrix is dou F dou x computed at steady state. Similarly, B matrix dou F dou d computed at S. So, now that means B matrix will consist of dou F1 dou d dou F2 dou d at steady state, and what is this? Let us find out. So, under steady state. Again, if you take this function, so that means what is my dou F1 dou d? So, if we take this particular term, it will be x2 steady state by L, correct, positive sign. So, it is a x2 by L, dou F1 dou d, dou F2 dou d, it is minus x1 by c, minus x1 by c. So, x2 is the steady state value of the capacitor current voltage, and x1 is the steady state value of the inductor current. What is C0 and what is E? What is E? E is nothing but dou F dou V in, right, which is nothing but dou F1 dou V in dou F2 dou V in. And if you go back, dou F1 dou V in, we can get it from here, but there is no V in term in the F2. So, this will be straight as 0, this is straight 1 by L, right. So, you got it, E matrix. What is C0 matrix? C0 is nothing but, what is that? Yeah, it is very simple, because here it is 0 1, that is it. So, you got all these matrix, and you can get different type of transfer function, right. So, you can get it. Okay. So, that means now once you have that x tilde dot is equal to, for any converter, x tilde plus b into d tilde plus e into v in tilde, and v0 tilde is c0 into x tilde, then I can take Laplace transform. Xx will be Si, you can minus A inverse B into d tilde s plus E into V tilde s, right, and then V0 tilde s is simply C0 into X0. Yeah, sorry, it was correct, S. So, then we can obtain different type of transfer function from here. So, finally, the model used for nonlinear control, we have three type of model: linear parameter varying model, because if we go to the A matrix for this boost converter, what we found, this is my A matrix, right. So, A matrix depends on the value of the inductor, which is generally fixed when the converter is designed, unless there is a variation of inductance when you operate close to the saturation point, otherwise they are more or less closely like more or less constant. Capacitance is also more or less constant, but D and R they vary. This is the operating point, that means duty ratio will vary based on your input output voltage relationship. Even for practical converter, we saw that if there is a load transient, R will definitely vary, and in addition to that, there will be variation of duty ratio, because the practical duty ratio will be slightly different from ideal. So, in order to anticipate that additional drop due to the the finite DC output impedance, you need to increase. Suppose if there is a load step up transient, your effective duty ratio has to be slightly higher than the ideal duty ratio to get the desired output voltage. So, that means duty ratio will also vary with the load current as well. Okay. So, that means that is why this is called linear parameter varying model, where A matrix is a function, it is a function of system parameters operating condition. Now, you can ask me, system parameter is generally L and C, and operating condition is the load resistance, the duty ratio, because that changes with the load current change, because those are the external parameters, right, in the change in input voltage, right. We also discussed average nonlinear model, where here we directly obtain x tilde dot is equal to A into x tilde. Okay, let me write it down here. We got x tilde equal to A into x tilde plus B into d tilde plus E into V tilde. In this case, we got x dot average is nothing but F average x tilde, and there is a duty ratio and input voltage. So, the difference between these two, this is this one, the first one, and the second one. And what is the third one? First, let us. So, third one is x dot, which is the actual switching converter with Q V. So, there are certain perspective. The number one input, it is only the deviation variable. Deviation variable is considered. Around deviation variable of what? Deviation variable of x average around x steady state. The model 2, it considers the average variable. Average quantity, and model 3 consider switching dynamics. So, in an effect, the third one is the most accurate one, but it is one of the most complex one because it was switching dynamics. Second one is a moderate, is reasonably good because you can vary the duty ratio, except for the saturation limit, we can widely vary, and this model can capture reasonably. But the first one is the simplest one, but it cannot capture for a duty ratio variation during transient. Thus, variation should be very, very small. but this we can apply our linear tools, like, because and here this is a linear parameter varying model. So, we can design compensator using our classical linear control theory toolbox, but model limit is a concern. This one is better than the first one, but it is a nonlinear model, smooth nonlinear model, where you can apply the traditional like a Lyapunov based, passivity based control, feedback linearization, okay, different type of control, which may be better than the linear control, but if we can tune the linear control properly, then you can get some closed behavior, at least somewhat better, but this may be better, you can get better transient response, but the switching dynamics is the one which takes care of the switching behavior, and it can get the performance, the fastest performance, which cannot be achieved either of these two techniques, using either these two models, I would say. So, the types of nonlinear model control depends on the model. So, first if you take linear parameter varying model, then we will take the average nonlinear model and the switching model. So, gain scheduling is a very popular technique. In fact, we have discussed the PID controller tuning using relay based tuning, Ziegler-Nichols. So, gain scheduling means we have talked about analytical controller design, right. We have voltage mode, current mode control, we have taken the small signal model, we have derived analytical way of compensator design to achieve certain crossover frequency, phase margin, and those equation can be used, the parameters, we can tune it in real time to get like a a reasonably fast transient for a wide range of operating condition. Another is the relay based tuning, but this is something like a offline tuning, and you have to put kind of a lookup table and update the parameter. Whereas the relay based tuning and something similar, they use online tuning. That means you can during the transient in the real time, you can create an event where you can inject like you can insert a on off nonlinearity, and using a control oscillation you can get the PID controller tuning parameter, and then you can plug in to get the transient response. But again, all these are somewhat complex method. The model predictive control, this once you get the linearized model, you can use a model predictive control for optimization, but the model predictive control can also be used using switching dynamics as well as average dynamics, okay. But in many paper actually the model predictive controls are used, because as if you are getting a linear model, so you can apply, you can obtain the discrete time model of the linear model, and you can obtain model predictive control for further optimization, because you can use kind of a state space based control technique, and you can optimize by creating some performance index. You can also use extended Kalman filter based method, because if you consider the stochastic system with unmodeled dynamics as well as the process, the measurement noise. So, then you can use the extended Kalman filter concept. But this technique again you can use you can linearize the system around some operating condition and then apply Kalman filter, right. So, it is an extended Kalman filter, that means linearize around it, consider the nonlinear average model, but you need to linearize. So, the model based average model, you can use a state feedback linearization, full state feedback, you can use output feedback linearization, you can use a passivity based control, you can use Lyapunov based control, and there are many other control techniques are there. So, I am just touching these two, I will discuss these two techniques in the subsequent lecture. Now, in switching control, you can use directly using switching like a sliding mode control, and that also we are going to discuss in the subsequent lecture. The boundary control is a class of switching like a sliding mode control, where we need to design the switching surface, and the switching surface can be the target trajectory itself. That means we want to design the switching surface in a way so that it will be the target trajectory itself. So, there will be no sliding motion, the sliding motion itself it will reach to the steady state. Then we will also talk about the PID controller nonlinear tuning, and this is one of the important topic which will be much more simpler. You can still use PID control, but we can incorporate the ripple parameter to get the performance which can be achieved by very fast like a sophisticated nonlinear control. But here we can simply use the same PWM controller because all this technique require like a maybe variable frequency operation or something like the structure, the surface of the controller can be higher order. So, it can require more resources, and most of the time we interface with this kind of control with a PWM control under steady state. So, they combine a nonlinear and linear control to achieve the desired response. But here what we are going to talk about is a single PWM control can achieve the whole performance. You do not need to do a separate controller, and you can also use the deadbeat control like a time optimal control you can do to achieve fastest response. So, with this I mean summarize state space modeling of switch mode power converter. We have discussed different types of models we have discussed. We have discussed the dynamics under switching as well as large signal, small signal model, and we have also given some overview of the nonlinear control using different model, and we have also discussed that if we want to simplify our control, then we can start with the simplest linear parameter varying model, but we need to update the parameter, but still the design is based on small signal. We can do average model, nonlinear model, and we can achieve something better, and then we can use nonlinear model, switching model, and we can get the fastest response, and all this we will discuss in the subsequent lecture. So, with this I will finish it here. Thank you very much.